In this video, we will discuss using buffered I/O in Power PMAC. First, we'll discuss a handful of problems that can be solved using buffered I/O. Then we'll discuss how to actually implement it. Finally, we'll discuss a couple of small notes about using buffered I/O. Let's look at a problem. In Power PMAC, most I/O is read and written as the code executes. This means that sometimes I/O may change while users are trying to use it. If this input toggles at just the right moment, it's possible that neither of these if statements execute or that both of these if statements execute. For users who are more familiar with traditional PLC programming, buffered I/O will be very familiar. Using buffered I/O, inputs and outputs will be read and written at the beginning and end of a scan, respectively. This means that there's no risk of I/O changing at unexpected times and generally makes the code more stable. This also means there's no risk of a race condition in which some I/O toggles before each other. All of them are read and written at the same time. Another common problem with reading inputs is related to signal bounce. When reading a physical switch, sometimes it may bounce or flicker true and false quickly when it's toggled. Alternately, maybe there's just noise on the signal. This signal can be debounced through programming. This is done by watching the signal for a certain number of cycles and comparing the values observed over time. If the value is consistent across all cycles, that'll be the new value used. However, if even one cycle is different, then no action occurs. Using buffered I/O, this can be done automatically. The third problem buffered I/O can address is edge detection, or using edge-triggered logic instead of level-triggered logic. In level-triggered logic, if an input signal is high, a user's code may perform one action, and if it's low, it would perform another action. If it's just setting an output flag, that's fine. Every scan it sees the signal is high, and it resets the output accordingly. However, some commands should only be issued one time, such as move commands. Issuing one repeatedly can cause unexpected or unwanted motion. Similarly, if the user is making a counter, it would keep counting as long as the signal is high, rather than once each time it goes high. By comparison, in edge-triggered logic, that code won't care if an input is high or low. Instead, it checks if it previously was high, but now is low, or vice versa. The logic will only trigger once as the input goes high, and then nothing else will happen until the input goes low. If a user wants their code to only trigger one time from an input, edge-triggered logic is the easiest way to do so. Instead of manually coding this, buffered I/O has pre-made structures for it. The last case we'll discuss is using buffered I/O for troubleshooting. Let's imagine that a user wants to test that their logic reacts correctly to inputs, but that the inputs aren't wired yet. In that case, they can use buffered I/O to tell PMAC to act as if a given input bit is true or false. Alternately, maybe they need to make sure a pump never turns off while they're testing one part of their system. Using buffered I/O, they can make sure that the correct output bit stays true or false, even if their logic would have turned that pump off. It lets them leave all of their code and pointers alone, but still temporarily overrule their sensors or outputs for their safety and convenience. In addition to all of those benefits, buffered I/O is also easy to use. Users must first point buffio-indexi.pin and buffio-indexi.pout to their desired input and output registers, respectively. Then, they can use buffio-indexi.in for inputs and buffio-indexi.out for outputs. Users can even access individual bits of these registers to read and write discrete I/O signals. Then, they can pick and choose what features they want to implement. Normally, each of these features takes significant PMAC code to implement, but by setting them up as buffered inputs and outputs, the firmware automatically scans them every background cycle. If they want some of them to scan on the RTI cycle instead, they can use sys.maxrtbuffin and sys.maxrtbuffout to do so. This will schedule the scans so they happen at a fixed frequency. It's especially helpful if the user is reading or writing to their I/O in a servo routine or foreground PLC. To debounce inputs automatically, a user can set buffio-indexi.inscans to a value of up to 3. This will force the firmware to watch the input for up to 3 scans and only change the value of buffio_indexi.in if the given bit was true for that long. If users want to use automatic edge detection, they have two options. If they know their code will check inputs every scan, they can use buffio_indexi.riseIn or buffio_indexi.fallIn. Bits of these will toggle when the corresponding bit of the input has risen or fallen respectively. If they are worried they might miss the transition, such as by being stuck in a while loop, they can instead watch buffio_indexi.riseIn latch or buffio_indexi.fallIn latch. These latch, staying true for multiple scans to make sure the user's code has time to react. Users will have to clear them, however. For troubleshooting, users can set buffio_indexi.forceIn on and buffio_indexi.forceIn off to overrule a sensor and force a given bit of an input to be true or false. Similarly, they can use buffio_indexi.forceOut on and buffio_indexi.forceOut off to force a given bit of an output to be true or false. Finally, there are some notes. In order for the firmware to perform these scans, users must set sys.buffioenable equal to 1. If they don't do this, the firmware will not scan and the data will not be used. Next, they can access the buffio structures from C using a pointer to shared memory. This lets them read and write to their buffered I/O from the C environment. Furthermore, users are limited to 64 buffered input registers and 64 buffered output registers. Users can access them as full register or bitwise. Last, for normal pointer variables used for I/O, when users declare them, they also give them a name. For buffered I/O, they would need to use a pound-defined statement in order to give them a user-selected name. They could also always use the buff.io structure to access the data, but that's far less user-friendly. We hope this video has answered any questions you may have about buffered I/O. If you still have any questions or concerns, feel free to reach out to an Omron representative.